Sylow theorem says if you have a prime number p and p to some power divides the size of your finite group, then that group has a subgroup of size p to the k. So there are three Sylow theorems. This is the first one. All of them have to do with subgroups of a finite group and a prime p. So let's prove this theorem. We're going to actually prove it by induction. The base case is when the group has size 1. It's just the identity element in the group. In that case, no prime power divides the size of the group, and so the statement is true vacuously. It's automatically true. So we're going to prove it by induction on the size of the group. The base case, the size equal 1, trivial. We're going to prove the theorem by remembering the class equation. We looked at this last quarter, but I'd like to remind you of what it was. So the class equation says the size of your group is the size of the center of the group plus the sizes of all other conjugacy classes with 2 or more elements. So this is the class equation. ZG, that's the center of the group. These contain elements that commute with everything in the group. These are conjugacy classes of size 2 or bigger. Now I'll remind you what the conjugacy class was. The conjugacy class containing an element X in your group, this is the set of all elements of the form Gx G inverse, where G is in your group. And this is actually the orbit of X under the group action of conjugation, meaning that your group action Gx is Gx G inverse. So the conjugacy class is this. Because it's an orbit, we can use the orbit stabilizer theorem. That says the size of the conjugacy class is the number of left cosets of the stabilizer subgroup in G. This is the size of G divided by the size of Gx. This Gx, to remind you, the stabilizer subgroup, that's the set of group elements that do not change X under this group action. So it's the set of group elements such that Gx G inverse is just equal to X. So we looked at all this last quarter, but I'd like to remind you because it's been a while. So we have the class equation. The size of the group is the size of the center plus the sizes of all conjugacy classes of size 2 or bigger. The way that we got this class equation was by just clumping together, unioning the conjugacy classes of size 1, that's the center of the group, and then writing down the rest of the conjugacy class sizes. Okay, so let's continue with the proof of the Sylow theorem. The proof is broken into 2 cases. So here's case 1. Case 1 is P does not divide the size of one of these conjugacy classes. So I have these conjugacy classes of size 2 or bigger. Case 1, P does not divide one of them. Well, in this case, because of this orbit stabilizer theorem, if P does not divide the size of the conjugacy class, P does not divide this division. But P does divide the size of the group. So that means all the powers of P that appear in the size of the group have to be canceled out by the size of this stabilizer subgroup. So that means that P to the K must divide the size of this stabilizer subgroup. So then we can proceed by induction on the group GX. We proceed by induction on the stabilizer subgroup. The stabilizer subgroup is a smaller group than G itself, so I can imply induction and we're done with the proof. GX will have a subgroup of size P to the K, and since GX is a subgroup of G, G will have a subgroup of size P to the K. Okay, so that's case 1. Case 2 is P divides CXI for all I. So back to the class equation, we have that in this case, P divides every one of these sizes. P also divides the size of G. So P divides the size of G. P divides all of these numbers. So P also has to divide the size of the center. The center of a group is a subgroup. It's a group itself. It's the set of all elements that commute with everything in your group. So we can apply Cauchy's theorem, our last video. There is an element A in the center with order P. This is actually why we proved Cauchy's theorem in the last video, for this step right here. Now, A is in the center of the group. It commutes with everything. So that means we can consider, by induction, we can look at the factor group. I'm going to look at the factor group, the set of cosets of the subgroup generated by A. So these are all powers of A. That's A to the 0, 1, 2, up to the P minus 1 power. It has order P. And because A is in the center, A commutes with everything else in G. That means this subgroup, the cyclic subgroup generated by A, is normal. I could form the factor group. This factor group has a smaller size than G, so I could use induction on the factor group. It's a group of a smaller size. The size of this factor group is the size of G divided by the size of A, so it's the size of G divided by P. I can use the induction hypothesis and say that this group has a subgroup, let's call it capital K, with P to the K minus 1 elements. I'm going to use this subgroup K in the factor group to come up with a subgroup of G of size P to the K. And so here it is. Here's the I'm going to use K to find a subgroup of G. I'm going to look at all group elements in G such that GA is in K. This is actually a subgroup of G. I can prove that in a slick way for you. Normally, if you want to prove something's a subgroup, you'd have to show that it's closed, it contains the identity, and it has inverses. And you could do that, but I will instead remark that this is really the inverse image of K under the natural homomorphism. So that kind of gets me out of having to prove it's a subgroup, because we know the inverse image of subgroups under any homomorphism is again a subgroup. So I'm not going to check the details, but you could if you'd like. So this is a subgroup of G. And I claim that this subgroup has p to the k elements in it. Well, here's how you can select an element in this subgroup. You could first select one of the cosets, one of the elements in K. There are p to the k minus 1 choices in there. So once you pick a coset, you could also pick a power of A to multiply with your G. So to count this, what I'm saying is this subgroup has p to the k elements. Why? Well, there are p to the k minus 1 choices for the coset GA. There are p choices of an element in the cyclic subgroup generated by A. I get to have one of the powers of A. This gives an element of the form G A to some power I in the inverse image under this K. You could check that this element is indeed in the inverse image, because we see that if I apply the natural homomorphism to something of this form, the natural homomorphism just takes your group element and assigns it to this coset. But powers of A are in this coset, so this is just the coset GA back. So I have p to the k minus 1 choices for the coset, and I have p choices for the A that can be possibly absorbed into the coset when I apply the natural homomorphism. And so therefore, the size of this subgroup has p to the k minus 1 times p, which is p to the k elements. So that's the end of the proof. That proof was a doozy. It was a little bit tricky. It's probably going to be the hardest theorem that we're going to see in the whole course, maybe, because it recalls a lot of stuff from last quarter. The class equation, conjugacy classes, the orbit stabilizer theorem, stabilizer subgroups, and the natural homomorphism and cosets. So this was quite a doozy, but you could always rewind the video, play it back, and email me with questions. All right, good luck.